Last time we finished with heat. What heat is and what it isn't. On that. There, most people use heat the wrong way. There, heat. When you put your hand on the table, heat is that energy that leaves your hands, and goes into the table. It's that heat that goes from one object to another object. It is not the energy in the object. Most people say, well, the hot object has lots of heat in it. No, it doesn't. What it does have is internal energy. Internal energy. And our internal energy, our symbol is a capital U. Our unit is the joule. Usually we could use calories. But usually you're going to see this joules. This is a big part. This is what, when we talk about the first law of thermodynamics, it's the change in internal energy that we're talking about. Change in internal energy is the total thermal energy of the object. And when we add heat to an object, internal energy goes up. When we remove heat from an object, the internal energy goes down. This is the sum of all the molecules, the sum of all those kinetic energies. In other words, Greek letter sigma, that's what this little E-shaped thing is, the Greek letter sigma. Sigma, mathematically it means sum. The sum of all the kinetic energies equals U. It also equals N, which is, say, the number of molecules, times a number K, which is a proportionality constant, called the Boltzmann constant, times T, temperature. So there is a relationship between the temperature. As U goes up, temperature is going to go up. As temperature goes down, up or down, U is going to go up or down. We're not going to worry about what the value for this constant is. It's just a constant that basically allows us to equate temperature to energy, just like we have a constant that allows us to equate force to mass and distance in that. But the idea here is seeing this, that there is this definite mathematical relationship between our internal energy and temperature. Remember, they are related. They aren't the same thing, but they are related. As temperature goes up, internal energy, and vice versa on that. Now, I'm going to show you this little video. Now, they kind of confuse the issue between heat and internal energy. What they're really getting at when they talk about heat is they're talking about the heat something can give up. In other words, how much is going to come out of the internal energy of that object. But they're really trying to get at internal energy in the whole thing, and though they don't call it that. Now, if you had coffee, if you're one of those people that likes to damage your coffee and put cream in it. Well, you have a hot coffee, you have your cold cream. When you put the cold cream in, those hot coffee atoms are going to give up energy to those cold cream atoms until they reach thermal equilibrium. In other words, there's heat energy that's going to flow from that cold to the hot, thus lowering the internal energy of the coffee and raising the internal energy of the cream. Even though it's this one big mixture, it will do that. Anyone need more time? So let's watch this little video.
Eureka! The story so far. When the degree of hotness or temperature of something goes up, its molecules go faster and it expands. This expansion can therefore be used to measure temperature itself. A device which does this is called a hotness meter or thermometer. On the Celsius scale thermometer, the level to which mercury contracts at the freezing point of water is labeled 0 degrees Celsius, and the level to which mercury expands at the boiling point of water is labeled 100 degrees Celsius. And now, temperature versus heat. Here's a bucket of hot water at 50 degrees Celsius. And here's a cup of freshly boiled water at 100 degrees Celsius. In which of these two containers are the water molecules moving faster? The bucket or the cup? That's right, because the degree of hotness of the water in the cup is much higher than the degree of hotness of the water in the bucket. And the hotter something is, the faster its molecules move. Would you say, therefore, that there's more hotness in the cup than in the bucket? In that case, if the water in your swimming pool is just a bit too cold for you, you'd be better off emptying the cup full of boiling water into it, rather than the bucket full of water at the lower temperature, wouldn't you? Or would you? You don't seem so sure. Let's do an experiment to find out. Suppose you had two identical swimming pools, one yellow and one blue. And suppose that the water in both of them was just a bit too cold for you. When you pour the cup of boiling water into the yellow pool, does the water feel any warmer? You can hardly feel any difference at all, can you? Now pour the bucketful of 50-degree water into the blue pool. How does that feel? Quite a bit warmer? Aha! So even though the water in the cup was considerably hotter than the water in the bucket, the 50-degree bucket water is much better at heating up swimming pools than the 100-degree cup water. Why is this? Well, let's look at the facts. The bucket obviously contains many, many more water molecules than the cup does. The temperature of the average molecule in the bucket is 50 degrees, and the temperature of the average molecule in the cup is 100 degrees. Now let's substitute something else for the molecules. Imagine that instead of molecules, the cup were filled with $100 bills, and the bucket with $50 bills. Which would you rather have? Each individual bill in the cup is worth much more than each individual bill in the bucket. But the total amount of money in the bucket is much greater than the total amount of money in the cup. It's the same with hotness. The degree of hotness, like the value of the dollar bills, is higher in the cup. But the quantity of hotness, like the quantity of dollar bills, is greater in the bucket. We know that it's the speed of the molecules that determines the degree of hotness of something. In fact, degree of hotness only depends on speed. It has nothing to do with how many molecules there are. Although the molecules in the bucket aren't going as fast as in the cup, there are more of them, so they more than make up in mass what they lack in speed. And it's mass, combined with speed, that determines quantity of hotness. We've already seen that the word for degree of hotness is temperature. Now it's time to introduce the other word for quantity of hotness, which is heat. The big difference between temperature and heat is that temperature depends on speed only, whereas heat depends on both mass and speed. The water in the cup has got a high temperature, but very little heat. And the water in the bucket has got a much lower temperature, but a great deal of heat. Now you know why buckets of 50-degree water are better at heating up swimming pools than cups of boiling water. On the other hand, if you're looking for somewhere to dunk your tea bag...
So, the idea here being, what we're really getting at here when they talked about heat, if I have an iceberg at 0 degrees, coffee is about 70 degrees, which is about what comes out of a coffee urn. There's our iceberg. Which is going to have a greater average kinetic energy? The coffee, right? That's our temperature. The coffee has a greater average kinetic energy. But remember, when you're talking temperature, how many molecules are you really talking about? One. The average one molecule. So, the average one molecule of our coffee has much greater than the average one molecule of our iceberg. However, internal energy. The iceberg. Why the iceberg? There's more of it. Even though add molecule for molecule, the coffee is greater. However, there's a lot more molecules. That was what they were getting with the analogy. Little cup full of $100 bills, great big bucket full of $50 bills, which is going to have more money. Great big bucket. Even though each one is smaller, there's a lot more of them. on that. This is really what the idea we're getting. It's the difference in internal energy on that. Questions? Now measuring heat. Well, when we measure heat, we use joules or calories. We actually introduce another energy unit here. Now, back in the day, energy was thought to be very different. In other words, you had thermal energy, which we measured in calories. You had mechanical energy, which maybe we measured in joules. You had electrical energy that had its own energy, but they were like little compartments. This energy and this energy and this energy. But they were different. Electrical energy, heat energy, all different. So the calorie. Now this is calorie with a small c. Very important. Or a big C, something different. Calorie is defined by the amount of heat energy to raise the temperature of 1 gram of pure water 1 degree Celsius. Whereas the joule is actually defined by work. Right? It's basically 1 Newton of force applied over a distance of 1 meter is 1 joule of work. That's what a joule is on that. However, our little calorie here is not a food calorie. That's calorie with a capital C, or a kilocalorie. 1 food calorie with a capital C is equal to 1,000 of these calories, or a kilocalorie. Alright, so food calorie is a little different on that. These are kind of part of the English system on that. One more time. So, then along comes James Joule. Now, Joule ran an experiment. He showed that heat and mechanical energy are the same. He had this little apparatus that basically, as these weights fall, they cause this paddle to turn. That's mechanical energy. Now, as this paddle turned through the water, the temperature of the water went up. The only way the temperature of the water is going to go up is if we are putting energy, we are increasing the internal energy of the water. In other words, this mechanical energy of the paddles is being converted to thermal energy in the water. This way, Joule showed that energy was energy. Specifically, he was working with heat and mechanical energy, but after this, we can say all energy is the same. We're just going from one form to another. And now we have what we call the mechanical equivalent of heat. 1 calorie equals 4.187 joules. In other words, 1 calorie, which is thermal energy, is equal to 4.187